In this webinar, I will be reviewing the new Octave Analysis features in ObserVIEW. I will discuss basic principles of Octave Analysis, some applications, and demonstrate how to complete this analysis using ObserVIEW. At the end, we will review a case study that was recently conducted to validate and demonstrate the Octave Analysis toolset in ObserVIEW. First, we start with vibration research's core focus and core values. Our core focus is to make the world's most innovative sound and vibration technology tools, enabling our customers to make reliable decisions and trustworthy products. Those core values are collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. These values govern our decision-making at a personal level and at a company level. Many of our values are apparent to our customers when they receive assistance from our support group or when they work with us as application engineers. But innovation is really the most evident in the products that we sell, whether that be our innovative control solutions that continue to improve test development methodology and running tests that are more realistic, or the tool sets that we've added to ObserVIEW, making things easier to do, easier to use, while still providing accurate, very precise results. So to get started, we'll talk a little bit about Octave Analysis. We'll look at some use cases of this software, talk about weighting functions, integration time, dB, and then we will jump into the case study. What is Octave Analysis in general? So Octave Analysis is typically used for noise or audio analysis, for troubleshooting, and for detecting where noises are occurring and what frequency ranges they might be happening in. It is a time-filtered result. What that means is the raw signal gets repeatedly passed through a series of time domain filters based on octavely spaced center frequencies. So each one of these bins has its own filter. The time waveform is passed through that filter, and the result of that filter, the actual measurement, gets plotted on a graph. That process gets repeated for every octavely spaced or third octave or sixth octave bin, depending on settings. And like I said, we can define these as one octave or a fraction of an octave, third, sixth, etc. With our new software, I've done up to 196th octave, but there is no limit other than the processing power of your PC. In the image that you see here, I'm using 1 octave spacing. So every center frequency is essentially a doubling of frequency. So there you can see the first 3 go from 4 to 8 to 16. The next would be 32 and then 64 and so on. Unlike the FFT, we see that these bins are not linearly spaced. An FFT has half hertz resolution or 1 hertz resolution, where all of the analysis lines are a fixed distance apart. In this case, our bins are octavely spaced. So 2 key differences from an FFT: the bins are not linearly spaced, the bins are proportional, and it is generated through time domain filters. This does have some benefits. The octave graph doesn't have any window functions that are applied, so that minimizes or effectively eliminates the leakage effects caused by windowing and the method that is used to generate an FFT. And it also allows for a faster update rate than an FFT. Here we can see the Octave Analysis weighting filters. This is common. The weighting filters are applied in order to replicate how the human ear experiences sound, or mimic how the human ear perceives sound. And these filters are specified in ISO 61260-1. And here you can see those three shapes on the left. You have Z weighting, which is essentially none, A weighting, and C weighting. When we talk about octave analysis, we're looking at decibel scale, and dB is essentially every 10 times you increase or decrease the dBA, the dB, there's going to be a 10x increase or decrease in intensity. So here you can see at the bottom, it's a linear dB. So 3 dB is a 2x multiplier. So if I have sound that is 3 dB louder, it's going to be 2 times louder. If it's 10 dB louder, it's going to be 10 times louder. And 20 dB, it's going to be 100 times. And on the right, we have just some general examples of real world items and what their dB would be, what that sound intensity would be. Now, this dB is looked at in two different ways. When we use octave analysis, you have a dB measurement for each individual bin, but we also have an overall intensity measurement that can be generated. And that gives you the overall intensity across the entire analysis frequency range. Some other parameters that we need to know when running octave analysis. Integration time. This is the time constant that is used for the moving average used to generate each of these octave bins. Very important if you have something that is relatively stable or slow moving, you can use longer integration time. But if you do have sharp events, then a shorter integration time is going to be necessary. We also have the ability to have averaging of the selection range. So this is where I highlight a series of time data, use a shorter integration time than the visible time window, and then average together each of those time windows to see what the average amplitude across that range of time is. And then finally, you have overall RMS or SPL. So when we are looking at sound measurements, we will automatically convert this to SPL. But normal acceleration, other type measurements are going to be just overall RMS. The total RMS for the integration period or frequency range is what is going to be displayed. And you can see that in the graph below on the left-hand side. This particular sound measurement, because it is a pressure measurement, has an dBA of 90.15. So that's a basic introduction to octave analysis. And overall, this process is relatively simple. Open a time waveform in ObserVIEW, generate the octave analysis graph, and then select the time range that you want to plot that data for. It's as simple as that. There are characteristics and things that we can modify that make it a bit more complex when you start talking about integration time and A weighting, C weighting, different filter shapes, etc. But overall, the general parameters are very simple to use and very easy to understand. As part of our development of this tool, as well as some validation, I went through my home wood shop and found a piece of equipment that needed to get repaired or updated anyway, and went through to compare the noise from a few different configurations of a DeWalt planer. Now this planer is a pretty common one for home woodworkers especially, and for hobbyists. So it's a very common piece of equipment, but one of the most common upgrades that is done is the actual blades on the right. The upper image is the 3-blade configuration. So those are 3 blades that run perpendicular to the path that the wood travels. And that is the factory setup. And in this case, I had old blades that were on the piece of equipment, new blades that I put on there, and then at the bottom you can see the new helical head. It's called the Helix head, segmented helical cutter head, that I put in after replacing the blade. So that's a newer type of cutter head, and it has a few benefits, but one of their primary claims to fame is a significant noise reduction when compared to the perpendicular blade type setup. So with that being one of their primary claims to fame, I figured I have the equipment, I might as well go and see what it looks like. So here's our basic test setup. I had a couple of accelerometers mounted on the planer itself. You can see my dust collection hose is in the way there, but I did have a planer or accelerometers mounted to the base as well as to one of the gearboxes. And then I also had a microphone mounted 4 feet away from the planer, from the outfeed side of the planer, and used those 3 measurement points for my validation and comparisons that you'll see coming up. Here's what the planer looks on the inside. A little dirty, but what do you expect? It's used to cut wood. You can see on the left hand side is the 3-blade configuration, so those blades run the full width of the planer bed and are perpendicular to the wood as it passes through. And then on the right hand side you can see that new helical head. This has a significant difference in that the blades don't meet perfectly perpendicular to the wood, so they have more of a shearing motion, as well as the number of blades that are constantly in contact with the wood. With the 3-blade configuration, you can see that every time one blade passes, there is a small gap before the next blade, and this can create noise. With the Helix head, there is always blade or blades in contact with the wood as soon as it starts. And that led to some interesting results that we will see. So here's our test sequence and kind of data collection setup. I used an Observer 1000, and in this case, with the new Octave Analysis tools, the Observer 1000 also qualifies as a Class 1 analyzer for sound. So the microphone was mounted about 4 feet away from the planer. We had those 2 triaxes. The board that I was planing is hardwood, and it's got a couple different types. So we have both cherry and walnut. And I removed as close to a 32nd of an inch per pass as I could. Used the manual wheel on the right hand side to make those adjustments. So there are definitely minor changes or minor differences in the depth of cut, but we repeated the cut multiple times to try get a relatively similar set of data. So 3 passes per sequence. And we look at test sequence 1 is the 3-blade cutter head with old blades. Now these old blades had planed a lot of hardwood and were ready to be replaced. They actually left a small line where there was a chip in some of the blades, and it was time for them to be replaced. The second sequence that I ran is with new blades, so same 3-blade cutter head but with brand new blades. And then the third was with this Helix cutter head. So let's look at some of this data. Each test sequence created a VFW. I went through and manually edited these and cut out a bunch of dead space, used the editor features of ObserVIEW to do that, and then also downsampled the waveform. In this older version of ObserVIEW that I'm using, we did not have the ability to automatically overlay multiple recordings. So I wanted all my recordings to start and finish at relatively the same time. So I cropped out the data that was interested, generated a CSV in Excel, and then imported it. Now with ObserVIEW 2022 that is set to be released soon, we will have the ability to overlay these files without having to use a CSV or to send it to Excel. So that's a new feature that will be coming out by early next year at the latest. And we look forward to that. I have it in beta and I was able to recreate this process through beta software. But in the end, we cropped out the events that were uninteresting, essentially the sitting at the noise floor or with just the machine running and dead space in between runs, and just cropped together all of the different passes for this hardwood. So a few things that are interesting when I look at this data, the PSD levels, you can see that there is a difference on the acceleration measurements. In general, the old blades were much higher. The new blades and the Helix are a little bit harder to differentiate. Those two lay upon each other pretty close. There's a few deviations, but overall they look very similar. And you can see in the GRMS measurements, this is on the bottom left, we went from 15 G's RMS on the old blades, again, knowing that those were bad and purposefully trying to find the worst case scenario, to 5 G's RMS to 3 G's RMS. An interesting thing to note is with the 3-blade time recordings on the top left and top right, what you see, those large spikes, are when the wood makes contact and leaves contact with the planar bed or with the actual blades. So you get a sharp audible spike as soon as that blade touches that wood, and then it planes, and then as it passes through, you get a sharp spike when it releases contact as well. And that carried over to the new blades as well. It wasn't as bad, but it definitely was still there. So that definitely added a lot of noise. Now if we look at the right hand side, you can see the microphone data, and even in the time waveform you can see that there is a significant difference. We talked about dB, dBA, and that linear scale. So here, when we look at the Octave Analysis graph in the bottom right, we go from 90.2 to 99.8 to 105.4. So you have significant changes there. If you go, it's well over 10 times quieter from the old blade to the Helix, and almost 10 times quieter or less sound intensity with the new blade to the Helix. So that is very significant, and having been in the shop running this equipment, I can tell you it is very significant. The noise reduction is apparent. So a significant reduction in noise and in vibration by changing to that Helix head. And the other thing that was really interesting, if we flip back here, you can see that that Helix head does not have that large spike when the boards make contact. Oddly enough, it actually gets slightly quieter when it is cutting. And the reason for that is because there are always knives in contact, but it's not losing contact or changing the amount of contact throughout the board's pass through the planer. So once there are boards in contact with knives, the cutting motion is not perfectly perpendicular, which reduces some of the noise. And also the fact that there are constantly blades, the same pressure is on that wood throughout the entire pass, significantly reduces the amount of noise and chatter that is generated by that cutting motion. So here's just a review. We can see the differences. And one other key note, I actually measured the noise floor of the system. So this is 2 recordings, one with the bass noise floor and dust collection and planar turned on, but no wood passing through it. That's the green trace. And the tan trace is our Shelix microphone from earlier. And oddly enough, there is actually a 3 dB decrease in sound intensity when the planar is cutting. So that is a 2x reduction in sound intensity when actually doing the work that it's supposed to be doing. Overall, very interesting and an excellent demonstration of how this software may be used. So if I open this data in ObserVIEW 2021, I can filter my traces down, and we will just look at these 3 sound traces. So these are our pressure measurements from all 3 cuts. And we can add a graph and look at the octave band graph. If I open that, I can see that octave graph. I can also change my weighting function in my trace properties. A, B, and C. I can change my integration time. I can not do an average. We have some defaults in here, 1, 3, 6, 12, and 24. You can see the effect of increasing or decreasing. I get a lot finer resolution. And I can add multiple traces if I want to compare. So if I edit my graph, I can go through and find my 3 microphone traces. Plot those all on, and my overall SPL can be enabled. I can see that and see that difference, as well as plot my audio frequency spectrum, so I have an idea of how my ear perceives this. So the bass tones, the mid tones, and the high tones. Overall, a very simple tool to use. You can take this data and copy and paste it out into Word or into Excel. All of those features continue to work. And it provides a simple to use method of analyzing any time history data that you might have. So this software can import any time history, any generic file format, CSV, UFF, WAV, RPC, and a whole variety more. If anyone has any questions or they want to try out this software, feel free to reach out to the sales team. We are always available and ready and willing to do demos, to answer questions, and even send out demo keys and demo licenses for you to try this out yourself. If you have ObserVIEW downloaded, you can activate the free 30-day demo through your key at any time. So don't hesitate to do that as well. In the end, download the latest version of ObserVIEW. It's available on our website. And check out the new Octave Analysis tool. Thank you, and have a good day.